All right, welcome everyone to today's TCS Plus talk. My name is Gautam. I will be the operator/moderator for today's talk. Behind the scenes at TCS Plus, we also have Clement Kenan, Oded Regev, Ilya Rosenstein, Anindya Day, and Thomas Vidic. I'm going to start by taking us around the table to introduce the different groups that are here today. So first off, we have Ben Lee and a group from Caltech. We have Josh, who's from CU Boulder. We have Sorokai at Aalto University. And we have the University of Toronto group, quite a big showing from Toronto. So those are the groups today. I also want to say that 2 weeks from now, we will have our season finale of TCS Plus, which will be John Wright at MIT presenting on this new result on NEEXP being contained in MIP star. So that should be very exciting. I hope many of you can join us for that. But enough of the future. We're going to talk about today's talk. Today, we're very lucky to have Lior Kamma, their speaker. Lior is a postdoc at Aarhus University. He finished his PhD with Robbie Krautgamer a few years ago at Weizmann. And his general research interests are in algorithms and data structures. Today in particular, he's going to tell us about lower bounds for multiplication via network coding. And without further ado, take it away. Thank you.
Thank you. Thanks for the invitation. So I'm going to talk about lower bounds for multiplication using network coding. This is joint work with Payman Afshani, Kasper Faxen, and Kasper Green-Larsen from Aarhus University. And let's start.
Lior, I think you managed to mute yourself. Can you unmute yourself?
Yep. I don't know how this happened.
Okay, no worries. If you could.
Yeah, so we have two integers, which is harder to do, to add them or to multiply them. Now, as you all know from grade school, hopefully, addition is quite short. Okay, we need only to do a constant amount of operations per digit, while multiplication is quite more involved. This is Kasper's doing, not mine, but so credit is due. And in fact, the classic algorithm for multiplying integers, it goes back to Babylonian times. So is it that multiplication is harder, or is it us? That is a question that kind of arose through the years. And as I said, the current multiplication algorithm originates in Babylon, although there they did it in base 60, which is similar to base 10 if you have your friends to multiply with. In 1960, Kolmogorov conjectured that multiplication of two n-bit numbers should take order of n squared operations. And he organized a seminar to prove this conjecture. A week into the seminar, a young student called Karatsuba proved, now a classic algorithm, I guess, that this can be done in much less than n squared. And the seminar was terminated. Its goal was unachieved. And this gave rise to major advances in the 60s and 70s. I'll just mention a few. So Toom and Cook presented an algorithm that takes this amount of time. And if I'm not mistaken, Toom gave the algorithm, Cook presented an adaptation for Turing machines. Shonahey and Strassen gave an even shorter running time, and they conjectured that the actual true complexity is n log n. Führer gave an even shorter running time, which was improved by Harvey and van der Hoeven through the years. So if you see here, there's a term of 2 to the O of log star. So between 2007 and 2019, Harvey and van der Hoeven have a series of papers improving that constant inside that OR notation. And eventually, very recently, they gave an algorithm that takes n log n time. All of these three algorithms are based on the FFT algorithm. And the last one is claimed to obtain also circuit complexity n log n. So yeah, let's discuss circuits. I wasn't sure about the background of the audience, so I'm just reviewing Boolean circuits very briefly. So a Boolean circuit consists of a directed acyclic graph with nodes are referred to as gates. We have input gates which have in degree 0, and output gates which have out degree 0. All the rest of the nodes are just called gates. With every gate, we assign a Boolean function, which if the in degree of the node is k, then the Boolean function takes k bits and outputs a bit. Okay, it can be any Boolean function. So and or, but not necessarily XOR, everything. Yeah, so this is the circuit. And intuitively, I'm not going to get into this formally, but there is a topological ordering which allows us to evaluate the circuit. I will show an illustration, but I'm not going to get into it very formally with indices. So suppose we have an input of 0, 1, 1, 1. These are the input gates. And we want to evaluate this node. So this node takes x2 and x4 and does the XOR of the two. Okay, similarly, the next node. And we go over all nodes. The topological ordering just guarantees that whenever we get to a node, all its input is already evaluated. Okay, and eventually we evaluate the output nodes. So I hope this is clear. I didn't dwell too much into it. There are several properties, interesting properties of Boolean circuit. One is the size, which is the number of nodes or edges that are in the circuit. The other is the depth, which is the longest input-output path in the circuit. And the fan in and out, which is the maximum in or out degree. Note that if we don't bound this and the circuit have arbitrary gates, arbitrary functions, then we could just connect all input to all outputs, and the circuit will be very small node-wise. It will have a lot of edges. Okay, so what is the network coding conjecture? Very intuitively, I'm going to give an intuition, and then I'm going to go and show a little example just to get a better feel of what it is. So the input for both problems is a graph with edge capacities, either directed or undirected, and we have k pairs of source and target. Okay, the pairs are not necessarily disjoint, but let's say that they are for ease of notation. The communication problem, again, intuitively, we want to transmit an R-bit message between each source and each target. And an edge cannot pass more information than its capacity. But nodes can manipulate messages. A node can decide to send a function of the messages that it gets. In the multi-commodity flow problem, it's very similar. We need to send R units of flow from each source to the target, but we cannot do any manipulation. And again, we cannot move more flow through an edge than its capacity. R is not necessarily an integer, just want to stress that. So a conjecture by Lee and Lee from 2004. This is the main conjecture in this in our paper. I mean, we rely centrally on this conjecture, is that in undirected graphs, the best flow rate equals the best communication rate. And let me illustrate it before going to our results. So let's say this is the input. So we have a directed graph, and we have edge capacities, and throughout the talk, edge capacities will be 1 unless stated otherwise explicitly. So yeah, this is a disclaimer. If I forgot to put a capacity, it's 1. Additionally, we have source target pairs. Okay, so in this case, we have 2. And for the communication problem, we think of an outside source giving a message to the sources in the graph. That's just easier to think about it like that. And each source chooses a message from a set of predefined messages randomly, and wants to transmit it through the graph source to the graph target. Okay, so let's focus on 0, 1. Messages. Every node receives a message and decides what to send onward through the edges going out of that node. So for example, the sources only know S1 and S2 respectively. They will send S1 and S2. Okay, if the graph is undirected, then a protocol essentially chooses an orientation. So there's always an orientation associated with a protocol. It doesn't have to be dictated by the graph if the graph is undirected. So S1 propagates the message S1 and S2 propagates S2. Now notice that middle node, it's going to send to its neighbor the XOR of the messages it got. Okay, and note that we never send more than 1 bit. So yeah, okay, sorry. In general, it's measured by the Shannon entropy. I forgot to say that. We will get back to that in a minute. So this node sends the XOR of both messages, and this propagates onward. And that way, T1 can now reconstruct S1, and T2 can now reconstruct S2. Okay, so notice that S1 is not directly connected to T1. Okay, is that clear? Any question? Just nod or something if everything is clear. Okay, good. I can't hear you, but I can see you. Yeah, so this is the communication problem, and apparently in directed graph, this freedom of manipulating the messages gives the communication much more power than flow. So the information rate of a graph is the best overall protocol, the best, the largest message I can send from sources to targets. Okay, and again, it's measured by the Shannon entropy. So in this graph, we get that the communication rate, sorry, is 1. Okay. Now, what about flow? So again, the same graph is the input with the same source sync pairs. And now we have 2 flows. S1 wants to send 1 unit of flow to T1, and S2 wants to send 1 unit of flow to T2. So a flow assigns for every commodity and every edge a value, okay, which we denote by F. Superscript J is the commodity, and UV is the edge. So again, we'll remove edge capacities just to make the drawing clear. The conservation rule says that whatever comes into a node has to come out of the node. If the node is not a terminal, it's not a source or a sink. And sources and sinks have to put 1 unit of flow. A source has to put 1 unit of flow into the graph, and a sink has to absorb 1 unit of flow from the graph. Okay, and that is so for every commodity. So now if we have 2 commodities, let's start by flowing F1. So the only thing we can do is flow through this middle bottleneck. Okay, because again, by the conservation, we cannot send anything from S1 to T1 to T2 directly, because this cannot be sent onwards. And so that is basically on this graph, it's the only way to define unit flow. Okay, is that clear? I hope so. If there are any questions, feel free to stop me. Okay, and if we want to send a unit flow from S2 to T2, we do the same, basically. Okay, so now we have both this flow, and I will remove the 0 flow just to make it clear. So we have both these flows. Okay, everything that is not here is just 0. So how much can we concurrently move with the graph? So we have this bottleneck. Okay, which again, the total amount of flow going through an edge cannot exceed its capacity. So we cannot move more units of flow through this edge more than 1. Okay, so the best rate we can get is 1/2 if each commodity sends 1/2 units to its target. Okay, each source sends 1/2 unit to its target. So we see that in directed graphs, the flow rate can be smaller. And again, because it is a simple graph, it's easy to see that it's the best we can get. So for a directed graph, we got that the best flow rate is smaller than the best communication rate. What about undirected graphs? So as you can see, there are edges here that we didn't use. So what if we remove the edge direction? So now we can do something else. So we can set 1/2 of the first commodity through the middle and 1/2 through the perimeter. Okay, and commodity, one rule in undirected graphs, again, like I said before, the flow actually chooses for each commodity a direction on the edge. Much like I said in the communication problem. Okay, but it doesn't have to be the same direction for all commodities. So in here we see that indeed F1 moves 1 unit of flow from S1 to T1, and the same way, slightly the same, moves from S2 to T2, and now we have both these flows and none of the edges exceed the capacities. Okay, so we get that the flow rate is 1 here. Okay, so going back to the conjecture, okay, so if I manage to convince you at least.
Sorry, I have a question.
Yeah.
Can you go back to the graph there?
Yes.
On that upper right edge, am I correct in understanding that because these are two different flows, that even though they're going in opposite directions, those two halves add up, they don't cancel out?
Yeah, because I only add, yeah, so in terms of the capacity of the edge, you mean?
Mm-hmm.
Then yes. So it is considered as 1/2 and another half going through the edge.
Okay, but yeah, as in usual flows, if it were the same commodity going both ways, they could cancel.
Yeah, so what I said was each commodity has to choose exactly one direction on each edge. We cannot have, because exactly what, like you said. So if it's a single commodity, then it chooses just one orientation. But if it's multi-commodity, then each commodity can choose its own.
Great, thanks.
No problem. Okay, so now restating the conjecture, in undirected graphs, the coding rate is exactly the same as the multi-commodity flow rate. Okay, so the conjecture is clear? Okay, I hope so. So our main theorem is probably the more exciting one, is that every Boolean circuit with bounded in and out degrees that computes multiplication, computes the product of two n-bit numbers, under this conjecture must have size at least n log n, asymptotically at least n log n. Okay, and one of the reasons it's exciting is that this is a result that actually people from the outside can understand. You can actually tell people that multiplication is harder than addition. So as for n squared, it was us and not the problem. It was the algorithm and not the problem. But according to this result, if we believe the undirected Peirce conjecture, multiplication is significantly harder than addition. So some known lower bounds on multiplication are known on very restrictive computation models. Sorry. So in 1998, Poncio proved that a lower bound for the size of read-once branching programs. This is a computation model composed of trees. And in 2011, Clifford and Yelsenius proved an omega n log n over w lower bound in the streaming variant in the cell probe model, meaning that this is a lower bound on the number of memory access required, where the memory, each word is consists of w bits. And the streaming model means that we see the multipliers digit by digit, and we have to report the next digit in the product before we see the next digit in the multipliers. Okay? Is there a question? Okay. Regarding the undirected pairs conjecture, so Adler et al. Showed that in directed graph, the gap that we show the gap of 2. So this gap can actually go up to omega, the size of the graph, up to asymptotically the size of the graph. So it's unbounded. Basically, they use the gadget that we showed, and they compose it in a subtle manner to show this result. And Braverman et al. Showed in 2017 that in fact it is enough to show that there is a very small gap, constant gap, between the communication flow and the communication rate and the flow rate in an undirected graph to imply that there exists an infinite family of graphs with larger gaps in the communication rate and the flow rate. The network coding conjecture, or the undirected pairs conjecture, was previously used to show lower bounds. In 2006, in the same paper, Adler et al. Showed lower bounds for oblivious algorithm computing the transpose of a matrix. An algorithm is oblivious if its memory accesses are settled in advance before seeing the input. So the memory cells that are probed are chosen before seeing the input. For Harvey et al. In 2019, a very recent paper, showed tight lower bounds for integer sorting in external memory model based on conjecture 1. Conjecture 1 is always the undirected pairs conjecture. And they also removed the obliviousness from the previous result. Yeah, so let's get to the main result. And in fact, we show a lower bound on a much simpler function, which is the shift problem. So the shift problem is defined as follows. So you get an n-bit number x, and you get an offset L, and you output a number, a 2n-bit number, which is basically the shift of x L bits leftwards or rightwards, depends on where you look from. But notice that this is exactly as multiplying x by 2 to the L. Okay, so this means that any circuit that computes multiplication can also compute the shift function. Okay, we therefore show this theorem, which is assuming conjecture 1, a Boolean circuit with bounded degrees that computes the shift problem has size at least n log n asymptotically. Okay, and this of course implies the first theorem. So before getting into the proof, is the statement clear? Okay, good. So the main idea in the proof is rather simple, surprisingly enough. The main idea is that because the graphs, the circuits have bounded degree, this means that a bounded neighborhood has very few nodes inside. Okay, so imagine a graph. We look at an undirected graph. This is a subtlety which we have to pay attention to. We go from directed to undirected graphs because we need to use, we want to use the conjecture. So let's say its maximal degree is at most C. And let's take one node U. And think of a ball around U with radius D, which is some positive integer or any positive number. It doesn't really matter. So in this neighborhood, there can be at most 2 times C to the D other nodes. Okay? Is this clear? So this means that no more than order of square root n lie within order of log n distance from U. Okay, so in other words, most of the nodes are very far from U. By far, I mean farther than half log n, where the log is based on, where the log base is C. Okay, so this is the idea, the main idea in the heart of the proof. So let's take a look at a circuit. So let's assume this is a directed circuit, okay? Computing the shift function. So we have n bit, an n bit input together with a shift L, and we have the output bits y1 to y2n. And we assume that this is bounded in and out degree. So if we remove the edge orientation just for a second, the induced undirected graph has degree at most c, okay, or 2c to be exact. And this means that if we look at this undirected graph as the induced undirected graph, at most 2 square root n of the output nodes, it should be y1, I'm sorry, within distance. This is exactly the idea I presented before. Okay, but this means that at least n minus 2 square root n are far from x1. And by averaging, we get that for at least 9/10 of the input nodes, that there exists a shift for which at least 9/10 of the input nodes are very far from their respective destination. Okay? And we fix this shift L. And let's say without loss of linearity that it's 0. It doesn't matter, it just simplifies the illustrations. Okay, and now we are back in the directed circuit. So now we hardwire that specific L0 into the circuit, which means that every node that had an incoming edge from one of the bits of L just fixes this bit as a constant, 0 in that case. Okay, because we fixed L0 to be 0. And now we remove L from our world. And now we have this graph that computes this circuit that computes the L0 shift. So basically, x1 moves its bit to y1, x2 to y2, and so on and so forth. Okay, and now we take this graph and think about it as a communication network. So we remove edge orientation again. Every edge is assigned capacity 1. And now we add sources and targets. Okay, each source wants to send 1 bit. And S1 is X1, Sj is Xj for all j, and Tj is Yj for all j, because we assumed L0 is 0. And now, by emulating the circuit as a communication network, this is the protocol of the network, we know that we can transfer 1 bit of information from the sources to their respective targets. So by emulating the circuit, we basically get that the communication rate of this graph is at least 1. And now we apply the conjecture. And if we change the setting, again, we don't change the graph, we don't change the source target pairs, we just change the settings, or the concept, the conceptual thinking of the graph. So we know by the conjecture that this graph has flow rate of at least 1, which in turn means that there exists a flow achieving rate 1. Now let's take a look at this flow. So we know that the number of edges is the sum of capacity because each edge had capacity 1. And we know since Fj is a legal, the ensemble of flows is a legal multi-commodity flow, and it has rate 1, then we know that this sum is smaller than the sum of capacities. But once again, recall that many of the sources were very far from their destination. So this unit of flow had to go very far into inside the graph. And that is why this sum has at least n log n. Yeah, it's at least n log n. So is this clear? And this means that the number of edges in C is at least n log n. Okay, and this settles the proof of the first theorem. If there are any questions, now is a good time. No? I hope that's because everything is clear. Our second result involves a special family of depth-free circuits. So let's present the family, and then I'll explain why it's an interesting family. So basically, we have the input gates, and we have the output gates. Again, for presentation, it's the same number. We will have twice the number of output gates as we have input gates, but this is just a small formality which can be rectified. It doesn't really change anything. And in the second layer, we have epsilon times a n gates, where epsilon is a constant smaller than 1. And another restriction on this type of circuits is that between x and y, if we remove the second layer and just look at the induced subgraph, we have a bounded degree subgraph. Okay, each node is of degree at most c. So why are these circuits interesting? So in 1977, Valiant showed that if a circuit has linear size and logarithmic depth, it can be reduced to exactly this type of circuit. So to a depth-free circuit with bounded degree on the input-output induced graph. Okay, and at most epsilon n gates in the second layer. This means that if we have lower bounds on these types of graphs, on these types of circuits, then this implies lower bounds on circuits of linear size and logarithmic depth. Okay, so the motivation is clear. In addition, 15 years afterwards, Valiant conjectured that if the induced degree between the input and the output nodes is at most 3, and epsilon is at most 1/2, then there exists a permutation that this topology, fixing the topology, we fix the graph, and we just change the protocol of the circuit, the gates assigned, the Boolean functions assigned to the gates. So this topology cannot compute some permutation. Okay? So this is a conjecture. It hasn't been proved or refuted since then. We take our second result takes a step further towards at least clarifying this conjecture. So our theorem states that if C is a depth-free circuit of this sort, meaning that the number of nodes in the second layer is at most epsilon n, so we have a slightly smaller constant epsilon. It's not half; it's 1/300. And the input-output degree is at most c. Then, assuming the network coding conjecture, we get that c is at least log n over log n. Okay, so let's revisit the conjecture for a second. So this was the conjecture, and what we show is that assuming the undirected pairs conjecture, this conjecture is true even for larger C and shift permutations only, although it's only for a smaller value of epsilon. The bound on epsilon is 1/300 and not 1/2. Okay, just to revisit the theorem. Okay, so again, this is the same sort of circuit, and we show, again, effectively we show that not only multiplication, but any shift, any circuit computing the shift function has to have this property that the degree has to be at least log n over log n. Okay? So this proof is a bit more involved, and I will explain why. So let's first see the circuit. Yeah, the drawing is going to be a little bit intimidating, so I pour it on the slide slowly. So we have the input and output layer, and we have the shift nodes, and we have this middle layer, F1 till F epsilon n. Between the input and output layer, we have at most degree C. And now we can assume without loss of generality, we have no restriction over the second layer, so we can assume that every input node connects to all of them and every output node connects to all of them. Of course, I didn't draw all the edges, but you can see where it's going and without all the mess on the slide. It's messy enough as it is. So yeah, at least the construction is clear. I mean, this is, the setting is clear. Okay, so we will show that every, assuming the undirected pairs conjecture, every circuit of this type that computes the shift function has to have large degree between the input and the output nodes. So this is our circuit, and once again, we want to use the idea that small degree implies small neighborhoods. But we have a problem, because in this graph, if we remove the edges, the edge orientations, not the edges, then every node, every input node is at most a distance 2 from any output node through the middle layer. So we need to somehow take care of it by removing that middle layer gently, ever so gently. So if we remove it for a second and just look at the undirected graph, then again, the same idea. Okay, at distance at most d, x1 has at most 2 times c to the d neighbors from y1 to y2n. And this means, again, that at most 2 square root n destinations are close, and therefore most of them are far. And again, by averaging, we have a shift L0 that sends the vast majority of pairs far. The vast majority of sources far from the destination. Okay, and again, without loss of generality, we will assume that that L0 is 0. So going back to the circuit, we hardwire this L0. Okay. So now we are still at the same problem we had before. That if I remove the edge orientation, every node, every input, every source is at most at distance 2 from every target. But since we have 2 to the n possible inputs and 2 to the epsilon n possible outcomes to the middle layer, we have a set of input that have a large set of inputs that all have the same outcome, the same function estimation for the middle layer, for that second layer. So there's at least one outcome, which is a sequence of epsilon n bits, which attain for at least 2 to the 1 minus epsilon times n of the inputs. So we hardwire this specific outcome. And let's denote this set of inputs by calligraphic F. Okay, we'll still need to deal with that. And then we hardwire that and we remove that from our circuit. So what did we get? Okay, if the input lies in F, then this circuit correctly computes the L0 shift, which basically means it transfers x1 to y1, x2 to y2, and so on. Right? Are we clear on that? Are we on the same page? Yeah. Now we remove edge orientation and add sources and destinations. And each source has 1-bit message. So what do we know so far? So if the string of the sources, the string composed by the sources, is in F, then the message they transmit to the source nodes is also in F. That means that in turn, the sources propagate this to the input to the circuit, and this is also in F. And thus, if we emulate the circuit, we get the correct output. But this is only for inputs in F. What happens if the string is not in F? So for that, we need to add another node, which will serve as a coordinator or a supervisor, depends on your preferences. And you intuitively make sure that whatever goes into the circuit, whatever x1 to xn get, is in F. And therefore, the circuit will do what it's supposed to do, the emulated circuit, at least. So how do we do that? We add edges of capacity 1 from each source to this coordinator U, which means, again, intuitively, U knows the true input of this communication network. U knows what bit each source needs to send to its respective target. And U finds a Hamming closest string S prime 1 till S prime n. And basically, it sends back to the nodes x1 to xn, it sends the information whether it needs to be whether the message has to be flipped or not in order to become S1 prime to Sn prime. Okay? And the intuition here is that if f is large, and we said that f is quite large, 2 to the 1 minus epsilon n, then for every string, for a random string of n bits, the Hamming distance from f should be small. And this leads with a little more work to the fact that the entropy of a closest string in f, the entropy of the distance is small. Okay, and basically this is the message that U sends to the x's, whether Sj should be flipped or not. Okay, this is a bit involved. Are we clear? Can I go on? Okay. So we add edges from U. Again, it's undirected, but intuitively from U to x1 to xn with capacities C1 to Cn, where Cj is the entropy of this indicator. Okay, so this is the capacity, and this is the Shannon entropy again. Okay, remember that the message we move through an edge in a communication network has to have its entropy smaller than the edge capacity. So if we indeed U sends to the x's the information of whether Sj is different from Sj prime, then this is enough. Okay? Then this capacity is sufficient. In addition, you will send the same information to the target nodes. Okay? And essentially, each target node now knows whether the message it got from the circuit or from the emulated circuit is the true message or it was flipped. And then it decides whether to flip it or not, and then we get the original message back. Okay? So these edges, the red edges also have capacities C1 to Cn, respectively. Okay? Is the construction clear? Okay. And then, again, intuitively, as I explained, emulating the circuit C gives us a solution to the communication problem. So each source transmits exactly 1 bit to its respective target. And therefore, this graph, which is an undirected graph, has communication rate at least 1. In turn, by the conjecture, this implies that the graph has flow rate at least 1. Okay, which means there exists a flow achieving flow rate 1. Okay? Now let's look at this flow. And what we want to do is do the same thing as before. We want to show that a lot of flow goes through the original graph, and for many nodes, it has to travel far. So how much flow can go through this new node U? So we want to show that not too much. So what's the capacity of the cut separating U from the graph? So we have n edges of capacity 1, so this is n. And additionally, we have 2 edges of capacity Cj for every j, where Cj is the entropy of this indicator. Okay, so this is the total sum of capacities of the edges around U. And a theorem proved by Harvey et al. Is that if F is a large set in a large subset of in 0, 1 to the n, then the expected distance of a randomly chosen, uniformly random chosen point is small. Okay, where epsilon is the parameter from the set. In turn, with some additional work, but not too much, this implies that the sum of entropies of these variables is small. Okay, this is just the original result with a little bit of technicalities, which I will not go into. But this means that for small enough epsilon, the cut around U is has no more capacities than 1.1 times n. Okay, and we control epsilon. That's why we needed to have epsilon smaller than 1/300, basically. So that means by the conservation, okay, remember that everything that goes into U has to go out because U is not a source nor a target. The total flow that can go through U is a little more than half of the flow. This means that if we remove U, at least 0.45, which is, again, it can be arbitrarily close to half, but slightly less than half of the flow goes through the original graph. So this means, again, by averaging, that for a constant fraction of source target pairs, we have that the source is far away from the target, and the source sends at least 1/10 units of flow through the original graph. Okay, this is simple averaging. This means, I will go over it now. So C times N is at least, at least the number of edges in the original graph. And this is because we had a degree bound. So in the induced graph by X and Y, every node was of degree at most C. Every edge has capacity 1, so this is exactly the sum of capacities over the edges. Since the flow had flow rate of 1, this is at least this amount. And again, since many sourcing pairs were far apart, that means that this sum is larger than n log to the base C of n. Okay, so if we look at the two edges of this calculation, we get that C is larger than log over the base of C to n. So this implies that C is at least log n over log n, asymptotically. Okay, and this implies the theorem. Is this clear? Note that yeah?
Yeah, so I realized there was a step a while back that I didn't quite follow, which was, when you had this intermediate node U,
yeah,
and you said, okay, for most inputs, the entropy of this indicator is small.
No, that's not for most inputs. The entropy is for a random curve.
Small, yeah. And then you said, okay, so on these, I think they were the red edges coming out of U.
Yeah.
That the capacity on them could essentially be this entropy.
Yeah.
But it seems like for any given input, you might still need to communicate a full bit. And
okay, so
are
yeah,
you like replicating the circuit here a bunch of times? How do you get away with this?
Yeah, so you caught me. I tried to cheat, so the slide is simpler. So in fact, what we do is if you collect, so it's not every bit for himself, but if you collect, let's say, 20 bits together, then you can show that not only the entropy is small, but you can get an encoding which is smaller. Okay, so I thought I could get away with it. Apparently I didn't, but formally this is correct, because formally all you need to show is that the entropy of the message is upper bounded by the capacity. This is the definition. But you're right, it feels like cheating. So yeah, in the paper we actually show that if you combine groups of 20 bits, also I don't remember the exact number, but a constant, a universal constant, then you can actually get an encoding from U to the sources that is actually shorter than the capacity.
Great, thanks.
No problem. One thing to notice is that, in fact, we didn't use the fact that each individual degree was bounded by C, just that the average degree is bounded by C. So, in fact, the theorem is even slightly stronger. Okay, and one other note is this can easily be turned into a shift, a cyclic shift permutation, and thus it relates back to Valiant's conjecture, which discussed permutations. Okay, so the fact that it's a shift from n bits to 2n bits, it's just to make the proof easier and more understandable. But it very small changes need to be done in order to fit it to permutation. So some notes about future work. So the undirected Peirce conjecture, it's not clear whether it's true or false. Yeah, this is something that would be interesting to know. There is evidence that on certain families of graphs it is true, but not in general. So certain families of bipartite graphs are known to hold that this conjecture holds, but nothing more that I know of. Valiant's conjectures. So specifically, this epsilon to the degree trade-off, which is still not clear. So our proof sheds light on this conjecture, but it doesn't prove nor disprove it. And last, are there any other interesting functions that have Boolean circuit complexity, omega and log n, assuming this conjecture? Yeah, and I think I'm done.
Thank you very much, Lior. We have some time for questions.
I was wondering, so here, I mean, it wasn't super crucial that you assume bounded degree, but you need neighborhoods to be small.
Yeah.
In the previous papers where they show circuit lower bounds from the undirected Peirce conjecture, do they have a similar assumption on their circuits?
So there was the previous lower bounds were not for circuits. The lower bounds I mentioned, the lower bounds I know of, are not for circuits. Therefore, I mean external memory models or the cell probe model, but not for circuits. In fact, oh, wait, yeah. So I said that there was a lower bound for matrix transpose. This is trivial in circuits, I think, because it's just sending the bit. So yeah, I don't remember now where it was, but anyway. So the previous lower bounds were not circuit lower bounds. But the work by Farhadi et al., they used similar methods to what we do. They used the bounded degree to show bounded neighborhood size, and that was the same. Similar, I mean, the same idea.
Great. Are there any other questions for Lior? Okay, we can stick around if anyone else has more questions offline, but I'll take us offline in a sec. I just want to remind people that 2 weeks from now, we have our grand finale of the season with John Wright telling us about an EEXP being contained in MIP star. So with that, thanks for coming.